Hello friends, in this video we are going to learn about an easy and interesting topic in network analysis, graph theory. ECE, EEE, E&A students and also the aspirants who are appearing for TRB exam, GATE, TANSET exams can make use of it. Let's start now. Network topology is the study of any electric circuit with the help of its graph. And we can analyze any complex electric circuit with the help of this. An important point to be noted here is this graph theory is applicable for non-planar network also. What does mean by non-planar network? How it differ from the planar network? A planar network is a network which can be drawn on a plane surface without any crossovers. For example, consider this electrical network. In this electrical network, the resistor R3 is seen to be crossing over the resistor R2. But I can redraw the same network like this, in which the resistor is not crossing the resistor R2. Okay, this is an example for planar network. This is an example for non-planar network because the resistor R1 and R2 are crossing each other. I cannot redraw this network in a plane surface without any crossovers. I cannot apply mesh analysis for analyzing this circuit because it is a non-planar circuit. So this is the advantage of graph theory over mesh analysis. Now see the steps to be followed when you are converting an electric circuit into its graph. First, replace all the elements by straight line or arc of the semicircle. All the elements in the electric network will be converted into straight line or semicircle, arc of the semicircle. And passive elements and voltage sources should be short circuited. What is passive element? An element which consumes energy in a network is known as passive element. Resistor, inductor, capacitor are the passive elements. So we should, suppose if we find any passive element in the electric circuit, we should convert it into short circuit in the graph. And we should open circuit the current source. Only current sources are open circuited in the graph, and we should retain all the nodes. If our original network, electrical network consisting of 5 nodes means our graph is also going to be consisting of 5 nodes. For an example, consider this electric network. In this network, there are 4 passive elements, 1 voltage source and 1 current source. So I have to convert these passive elements and voltage sources into short circuited lines, and I have to open circuit the current source. So I will get the graph, and I should retain all the nodes, right? So 1, 2, 3, 4 are the nodes. So I have mentioned all the nodes by dots. So it is not necessary to represent these open circuited path. Now consider another example. Look at this network. In this network there are 5 nodes, and I have mentioned all the 5 nodes by numbers in the graph. I have retained all the nodes, and I have short circuited all the passive elements, resistors and capacitors, and also the short circuit. Now count the number of branches. The number of branches in the graph will be less than or equal to the number of branches in the original network. In the first network, there were 6 branches, and its corresponding graph consists of only 5 branches. And the second network consists of totally 6 branches, and its graph consists of again 6 branches. So it is to be remembered that the nodes will be always equal in graph and its corresponding original network, but the branches in the graph will be less than or equal to the number of branches in the electrical network. There were 4 types of graphs: unconnected graph, connected graph, undirected graph, and directed graph or digraph or oriented graph. If all the nodes of a graph have been connected by at least one branch, then it will be called as connected branch. Otherwise, it is unconnected graph. In this graph, see here, the node 5 is not connected by any branch. So, it is an unconnected branch. Suppose I make a connection between 5 and 4 nodes, then it will become a connected graph. And if I have mentioned the direction of the current flow in each and every branch by arrow, then it is known as directed graph. Otherwise, it is called as undirected graph. So this is an example for undirected graph, and this one is the example for directed graph. Next is subgraph and its types. Subgraph is nothing but a part of a graph. There are 2 types of subgraphs. One is tree and co-tree. Tree is a connected subgraph. That means it consists of all the nodes from its original graph. there will not be any loop in a tree, so that there will not be any loop current flowing through the tree branches. We can call the branches by name twigs, and it should be represented by solid lines. Total number of twigs in a tree will be n minus 1, where n is the total number of nodes in the original graph. We can have n power n minus 2 number of tree for a given graph. There is another one formula to find number of trees in a graph, that is determinant of A into A transpose, where A is the reduced incidence matrix, which we can learn later. For example, consider this graph. These three are the subgraphs of this graph. All three are connected subgraph, but in this case there is a loop formed, so it is not a tree. These two are considered to be the tree of the given graph. Consider this graph and two of its subgraph. In this case there is no loop formed, but a tree is a connected subgraph, right? All the nodes should be connected directly or indirectly, but in this case A and D are connected individually and B and C are connected individually, but there is no interconnection between all the four nodes, so it is not a tree. In this case there is no loop formed and all the four nodes are connected, so this is a tree of the given graph. Co-tree is a complement of the given tree. Its branches are called as links or cords, and we represent these co-tree by dotted lines. An important point here is a co-tree need not to be a connected graph, which means loops may be formed. You can see here a graph. I have drawn one of its tree. When I remove the branches of this tree from the original graph, I will get my co-tree. A graph consists of totally b number of branches. A tree consists of n minus 1 number of branches. So number of branches in a co-tree will be b minus n minus 1, right? So total number of branches in a co-tree, L will be equal to b minus n minus 1, where L is the number of link, b is the total number of branches in the original graph, n is the total number of nodes in the original graph. We can move on to next topic, incidence matrix. Otherwise it is known as augmented incidence matrix. It is represented by a letter A, capital A. The word incidence means connection of branches to a particular node. Suppose if our graph consists of n number of nodes and b number of branches, then our incidence matrix will contain n number of rows and b number of columns. So the order of our matrix will be n by b. N is the number of nodes, b is the number of branches in the graph. The elements of our incidence matrix will be plus 1, minus 1 and also 0. Our matrix element value will take the plus 1 if the branch current is leaving a node, and its value will be minus 1 if the branch current is entering a node, and its value will be 0 if the branch current neither enters nor leaves a node. Total number of branches incident on a node is known as degree of the node. Suppose two branches are connected at a node, then the degree of the node will be 2. 3 elements are connected at a particular node means the degree of the node is 3. Let us write the incidence matrix for the given graph. In this graph there are 4 nodes and 7 branches. So my incidence matrix will contain 4 number of rows and 7 number of columns. The first row of our incidence matrix corresponds to the first node in the graph, node 1 in the graph. When I am considering this node, A, B, C are the branch currents which are leaving the node. So I have to put plus 1 value for those branches. 1 plus 1 for A, B and C. And I am considering E branch current, it is entering the node 1. So I have to put minus 1 value for the corresponding branch. And D, F and G are not incident at node 1. So they take the value 0. Similarly, when I am considering node 2, there are 3 branches incident at the node. C is the entering branch current and D and F are the leaving current. So D and F will take the values plus 1. D, F plus 1 value. C is entering, so it will take the value minus 1. All the other 4 branches are not incident at node 2, so they take the value 0. Similarly, I can write the elements for the third row also. What about fourth node? Degree of the node is 3. There are
2 currents entering the node and E is leaving branch current. So E will take the value plus 1 because leaving branch currents takes the value plus 1. F and G will take the value minus 1. And all other 4 branches take value 0 because they are not incident at node 4. Our incidence matrix possesses some properties. First property is that each column representing a branch contains only 2 non-zero entries plus 1 and minus 1, the rest being 0. The unit entries identify the nodes between which it is connected. You can check here. In this incidence matrix, when you are looking up all the column elements, there are only 2 non-zero entries. 2 non-zero elements only. All the other elements will be 0. When I am considering the column 1A, first column A, which is corresponds to the branch A, the nodes between which it is connected is 1 and 3. So 1 and 3 are the connecting nodes of branch A. Next property, unit entries in a row identify the branches incident the node. When I am considering this same incidence matrix, when I am checking out the third row wise I am counting the unit entries 1, 2, 3 and 4. There are 4 non-zero entries. So the degree of the node 3 will be 4. That means 4 branches will be incidenting at the node 3. If the degree of a node is 2 means the branches incidenting at that particular node are in series. Next property, columns with unit entries in 2 identical rows indicate parallel branches. Observe the first 2 columns of our incidence matrix, A and B. They took the values similarly because first row they took the value plus 1, second row 0, third row minus 1 and fourth row they took the value 0. And observe here the A and B are parallel. A and B branches are parallel because they are connected in between 1 and 3 nodes. So from a given incidence matrix you can construct its graph. So that's the next property. If you are deleting a particular row from an incidence matrix, you will get a reduced incidence matrix. It will be represented by A dash. The node corresponds to the row you have deleted will be considered as reference node. Already we have learned that column wise our incidence matrix consists of 2 non-zero entries plus 1 and minus 1. So when you are adding all the elements column wise, the answer will be 0. So this property helps us to write the incidence matrix from the reduced incidence matrix. For example, I have written a incidence matrix from its reduced incidence matrix. I have checked the first column and summed up all the elements. 1 plus 0 plus 0, I have got 1. But the total should be 0, so I have included minus 1 here. And next column, the sum is 0 plus minus 1 plus 1, 0 I have got. The sum should be 0, so I have put the value 0 here. Similarly, I have written the element values for the third and fourth columns also. Shall we draw the graph for this incidence matrix? So there are 4 rows. So there should be 4 nodes 1, 2, 3 and 4. And there are 4 columns. So there should be 4 branches A, B, C and D. So I have mentioned 4 nodes here. 1, 2, 3 and 4. So the first column corresponds to the branch A, which is connected between the nodes 1 and 4. So I should draw a straight line between 1 and 4. Check the sign here. Here the node 4 is minus 1. That means the branch current A is entering the node 4 and leaving the node 1. Our branch current A is leaving node 1 and entering the node 4. And the second column B branch connected between the nodes 2 and 3. 2 and 3. I will draw a semicircle here. And my branch current B is leaving node 3 and entering node 2. So B branch current is leaving the node node 3 and entering the node 2. And third column corresponds to branch C, and branch C is connected between nodes 1 and 3. C is connected between 1 and 3. I have drawn a straight line here, and the current enters node 3 and leaves node C. So leaves the node 1 and enters the node 3. And branch D is connected between 1 and 4. Node 1 and 4, and the current leaves the node 4 and enters node 1. So this is the graph of the corresponding incidence matrix. Next is fundamental loop matrix. Its another name tie-set matrix, circuit matrix. What is fundamental loop? See the definition. A loop contains only one link and one or more twigs. What is link? It is a branch of a code tree. What is twig? It is a branch of a tree. So when you are writing a fundamental loop matrix for a graph, you should consider a tree and its corresponding code tree. We can draw n power n minus 2 number of trees for a graph. I have drawn a tree and its corresponding code tree. In this case, A, D and E are the twigs, and B, C and F are the links. If we connect the link B in its original position, here a loop will be formed, right? That is known as a fundamental loop. If I connect the branch C here, then also a loop formed, that is fundamental loop 2. And when I am connecting this F here, another one loop formed, that is fundamental loop 3. So for this tree, I can have 3 fundamental loops. Our tie-set matrix gives the relation between the link current and the branch currents. Row size is equal to the number of fundamental loops, and column size is equal to number of branches in the original graph, total number of branches in the original graph. So what will be the order of our matrix? Row size is number of fundamental loops, which is equal to number of links, that is B minus n plus 1. Already we have learned that, no? So the order of our matrix will be number of fundamental loops, which is equal to number of links, that is B minus n plus 1 by total number of branches in our graph. So B minus n plus 1 by B will be the order of our matrix, and our matrix elements will be same as that of incidence matrix, plus 1, minus 1 and 0. The link which makes the fundamental loops takes the value plus 1. And twigs and links which are not part of the fundamental loop takes the value 0. Similarly, if the branch current direction of a selected fundamental loop is same as that of link current direction, then it takes the value plus 1, otherwise it takes the value minus 1. We shall write the tie-set matrix for this graph, and I have selected a tree from this graph that is represented by solid lines, and dotted lines represents its code tree. So A, B and F are the twigs, and C, E and D are the links. First I am connecting the link C in its original position here. So when I am connecting a link here, so a fundamental loop 1 is formed. Then I am connecting the link E here. So I am getting second fundamental loop here. Then I am connecting the third link D here. So I'll be getting third loop like this, that is fundamental loop 3. The branches A, B and C make the first fundamental loop. The remaining branches D, E and F are not the part of the fundamental loop. So they take the value 0 here, and the link corresponding to this fundamental loop is C. So it takes the value plus 1. Then I am checking the direction of other two branches. Branch currents. B's direction is as same as that of the C's direction, same direction. So B takes the value plus 1, but A is opposite to that of the C. So A takes the value minus 1. Next I connect the second link here. Second link is E. So fundamental loop 2 is formed here. Branches A, B, E E and F make the fundamental loop to 2. So the remaining branches are D and C. So the branches D and C takes the value 0, and the link corresponding to this fundamental loop is E, so it takes the value +1. Now check the direction of other branch currents. F and A are opposite to that of E's direction, but B's direction is same as that of E. So B takes the value +1 and other branches takes the value -1. Similarly, I can write the elements for the third row also. A graph contains n power n minus 2 number of trees, so that I can write n power n minus 2 number of die-set matrix for a given graph. Next is fundamental cut-set matrix. A fundamental cut-set contains only one twig and one or more links. Number of fundamental cut sets is equal to number of twigs of a tree. So our matrix gives the relationship between the branch voltage and twig voltage. In this matrix, row represents the fundamental cut set and column represents the number of branches in the original graph. So the order of the matrix will be n minus 1 because the total number of twigs will be n minus 1. So the order of our matrix will be n minus 1 by B. The elements of our matrix are same as that of the previous matrices, +1, -1 and 0. 1 for the selected twig of a particular fundamental cut set, 0 for all other links and twigs which are not part of the fundamental cut set, and the element takes the value +1 if the direction of link current of selected fundamental cut set same as that of the fundamental cut set twig current. Otherwise, the value will be -1. For example, consider the same previous graph. From the graph, I have selected a tree whose branches are D, E and F. So this is the tree I am considering now from this given graph. A cut set contains only one twig and one or more links, right? Now I select one of the tree branch D and cut it along with the links connected with it A and B. So my graph will be divided into two parts, and this part is known as fundamental cut set. The direction of the cut set will be same as that of the current direction of the tree branch I have selected. That is, the direction of this cut set is same as that of the direction of D branch. The fundamental cut set's direction is represented by the pink arrow lines. The branches which are the part of this cut set are A, B and D. So all other branches C, E, F takes the value 0 in matrix. The branch D takes the value 1 because it is the branch that is considered for this fundamental cut set. So D takes the value +1. Then I have to check the cut set's directions and the link current directions. So cut set direction is like this direction, and A and B's direction are opposite to that of the cut set's direction. So I have to put a value -1 for A and B. So -1 for A and B. That's all, friends. I hope you may get a clear idea about this topic now. I give you some practice questions. Try to solve them. We shall discuss the solution in the next video. Thank you.